Hi guys, this is Mrs. Cook. We've talked about the general layout of the periodic table and how it can be a really useful tool to know similar properties between elements, as well as just organize the elements in terms of their atomic number. In this lecture, we're going to learn about other trends that we can determine based on where elements are on the periodic table. So we've already talked about metallic character, and so we know that elements that are more metallic are going to be towards the right side of the periodic table, and our non-metals are over here, and so metallic character will decrease as you move from left to right on the periodic table. Some other trends that we're going to focus on in this lecture are specifically the ionization energy. So we're going to talk about what that means, and we're also going to talk about atomic radius as well as electronegativity. There are numerous trends that we could talk about. We're just going to focus on those three in this lecture. The first trend that we're going to talk about is atomic radius. So an element's position on the periodic table can help us to determine the size of the atom of that particular element. So before we can talk about the trend, we have to understand what atomic radius is. It's the size of an atom. So if you remember anything from last unit, we know that atoms have a nucleus, and in the nucleus we have the protons and we have the neutrons. And then outside of that nucleus, we have electrons that are scattered and moving around that nucleus. So you might be thinking to yourself, well, how can we determine the size of an atom if we don't really know where that outer edge is? The radius of an atom is determined by half of the distance between the two nuclei and two adjacent atoms. So like this picture below. So we can identify where the nucleus is, and then the distance between those two nuclei can then be measured. If we know the distance between the two nuclei, we can essentially cut that in half to determine what the radius of the individual atom would be. So as I was saying before, it's impossible to measure the radius of one individual atom. We need to have two comparative points, or the two nuclei, in order to determine the radius of an atom. Now that you have a rough idea of how the atomic radius is determined, we can look at the trend of atomic radius on the periodic table. So most physical properties are dependent on the size of the atom. So things like melting point, boiling point, and density are dependent on the size of the atom. The trend is as follows. As we move down a row on the periodic table, we have increasing atomic radius. And that should make sense because we know that electrons, as we're moving down that periodic table, we're adding energy levels to the atom. So if we quickly just look at the trend from lithium to sodium as we move down that column, we know from last unit that lithium has two energy levels, so 2 electrons on that first energy level and 1 on that second, where sodium has 2 on the first, 8 on the second, and then 1 in that third energy level. So that addition, that added third energy level, essentially makes the atomic radii larger in sodium, and then we see that same trend as we move down the periodic table in all of these rows. So you can really see the trend in increasing atomic radius as we move down. All right, so now let's talk about the trend as we move across a period. So as we move from left to right across a period, we have a decrease in atomic radius. So we can see that as we start here with lithium and we move across the periodic table, we have a decreasing atomic radius. Let's talk about that. All right, so let's look at the trend based on what's happening between lithium, beryllium, and boron. So we see a decrease in atomic radius as we go from lithium to beryllium to boron. In order for us to understand this, let's compare and contrast like similarities and differences. We can clearly see that in lithium, Arrange the following atoms in increasing atomic radius: phosphorus, silicon, and nitrogen. In order for us to answer this question, we have to evaluate. So we notice that nitrogen and phosphorus are in the same group, meaning the same family, going in a column. And so because nitrogen is in the second energy level and phosphorus is in the third, we can then say that nitrogen has the smaller radius than phosphorus. So nitrogen only has 2 rings, whereas phosphorus will have 3 rings, therefore nitrogen has the smaller radius. Then we can compare silicon and phosphorus. Silicon and phosphorus are in the same period. So we know for sure that nitrogen is going to be the smallest, but now we need to figure out which order the phosphorus and silicon are in. And so because they're in the same period and silicon is to the left of the phosphorus is also smaller. And so we can say that then nitrogen is the smallest, and then we have phosphorus, and then finally silicon. So you guys should be able to evaluate the atomic radius of elements the same way that I just demonstrated in this problem. The next trend we're going to discuss is ionization energy. Ionization energy is the amount of energy needed to remove an electron from an atom in a ground state. So that's essentially saying when an element is stable, when it's in its natural state of solid, liquid, or gas, how much energy is required to remove one of those outer electrons. You might be thinking, okay, so how do we get an electron to be removed from an atom? Well, we have to add a source of energy. This is a complicated process, but heat or an electrical current could be added in order to measure this ionization energy, and this is something that we talk more about in AP. For now, you just have to understand that ionization energy is the amount of energy needed to remove that electron from an atom. A few important points before we talk about the trend is that the valence, or the outer electrons, will always be removed from the atom first. So it takes less energy to remove those valence electrons, and so those will be the electrons that are able to be ionized first. When an electron is removed from an atom, it becomes a cation, or it becomes more positively charged. So let's use lithium again as an example to help us understand this. This says after the first electron is removed, it gets harder to remove the second and third electron. So if we were to add, let's say, an electrical current to lithium metal, and we were able to remove this electron, we call this the first ionization energy, or the amount of energy to remove that first electron. After we remove that first electron, we now only have 2 electrons, but we have 3 protons, which is why a +1 charge cation forms, because we have the 3 protons and only 2 electrons. If we were to add a greater amount of energy, enough energy to remove a second electron, we would call this the second ionization energy, and that second ionization energy is always going to be greater than the first ionization energy. The nucleus is going to hold on even tighter to its 2 electrons once it's already lost 1 electron. So if lithium would lose this first electron and then a second electron, it would then become a +2 charge. And so lithium would still have its 3 protons, that's what identifies the element, but it would only have 1 electron left. So here I'm just explaining why it gets harder to remove the second and third electrons. There are always going to be the same number of protons because protons identify what the element is. And so the more electrons that you remove, the nucleus is going to hold on tighter to the electrons that it has left, requiring a greater ionization energy to remove those additional electrons. So now that we have an idea of what ionization energy is, let's talk about the trend across the periodic table. I want to note here that we're only talking about the first ionization energy. So we're only talking about, in this graph, and really the only thing that we're talking about in honors in general chemistry overall is the first ionization energy. Okay, so this graph here is showing us the ionization energy in comparison to the atomic number. So we know that on that first energy level, the only two elements on that first energy level are hydrogen and helium. And let me use a different color so we can see this a bit better. So we only have hydrogen and helium. And we can see that as we move from left to right, or as we go from hydrogen to helium on the periodic table, we have an increase in ionization energy. But when we go down to that second energy level, which starts with lithium, we notice that we have a big decrease. So as we go from helium and then we go down a period, the lithium, or the ionization energy, will decrease as we go down a column. And then we have this general increase as we move from lithium all the way to neon. Again, so let me draw that trend again. So that's the second energy level. The third energy level, which goes from sodium to argon, we have a general increase, potassium to krypton, and then so on and so forth, all the way down our 7 periods. So as we move across a period, we have an increase in ionization energy, but as we go down a family or a group, we have a decrease in ionization energy. And you can see from this data that it's definitely not perfect. So it's not a rule, but it is a trend. And so we do see these little dips here, which we talk about why those dips happen in AP chemistry, but it's not something that you need to know for honors chemistry. So to summarize ionization energy, noble gases are going to have the highest value of ionization energy. Noble gases are stable. They have a full valence shell, and so it's hardest to remove those electrons. The alkali metals are going to have the lowest ionization energy. We know that the alkali metals have only one valence electron, and so it's easier to remove that valence electron because the atom doesn't hold on to it as tight. It wants to get rid of it so that it has a full valence shell. There is a relationship between atomic radius and ionization energy. The larger the atomic radius, the lower the ionization energy, and the smaller the atomic radius, the higher the ionization energy. Now, if we think about how the nucleus holds on to its outer electrons, it should make sense that ionization energy decreases as we move down because those valence electrons in the lower periods of the periodic table, they're really far away from the nucleus. The nucleus doesn't have as strong of a hold on those valence electrons, and so it doesn't require as much ionization energy to then remove those electrons. The increase across a period in ionization energy should also make sense based on what we were talking about in terms of Coulombic attraction. If we're moving across a period, the valence electrons are still in that same energy level. So we talked about the second energy level, and we talked about how lithium, beryllium, and boron all have valence electrons in their second energy level. But the addition of protons as you move across the periodic table makes the nucleus hold on tighter to those valence electrons in the second energy level. So as we move from left to right, there's going to be an increase in the ionization energy because the nucleus is holding on tighter to its valence electrons. So it's going to require more energy to then remove those valence electrons. Our third and final periodic trend is electronegativity. We're going to talk a lot more about electronegativity next unit when we start to get into bonding, but electronegativity is the ability of an atom to control electrons within a chemical bond. So we haven't talked about chemical bonds yet. We've been focusing a lot on just elements by themselves. But we can start to learn about the trend so that we can apply it next unit. Electronegativity is a comparative measure, so it can only be measured relative to other elements. Electronegativity values have been based on a measure that's related directly to fluorine. So fluorine is the most electronegative element, and the value of 4 has been assigned to fluorine. So if fluorine has an electronegativity value of 4, fluorine being our most electronegative, and it has an electronegativity value of 4, all of the other elements in the periodic table have been assigned a ranking of electronegativity based on that fluorine's ability to control electrons within a bond. Atoms with a higher electronegativity will have the most control of electrons in a bond. So you can look at electronegativity values, and based on those electronegativity values, you can determine the polarity of a structure, which we'll talk more about next unit. And you can also basically determine which of the elements within the bonds are going to control the electrons in the bonds more. So here's a nice picture. So we can see purple to blue to light blue to green to yellow to red. This is an increasing in electronegativity. And so fluorine we know is the most electronegative element. And we can clearly see that, number one, the noble gases have no electronegativity. So they have no attraction for elements within a bond. They're stable. They don't want to form bonds. So they really have electronegativity values of 0. But then the other elements, the lowest electronegativity values are found down here in the left-hand corner. And then we have a general increase in electronegativity as we move up, and a general increase in electronegativity as we move across. So as we move from left to right on the periodic table, we have an increase in electronegativity. And as we move from the bottom up, we also have an increase in electronegativity. So you could look up electronegativity values, and you would notice that oxygen is here in this orangish range, whereas hydrogen is more in this greenish range, which tells us that oxygen is more electronegative. So as I stated before, fluorine is the most electronegative element. So then based on that, if you have a water molecule, which atom would have the most control of the electrons? The answer to that is oxygen, but let's examine that. Electronegative, it's going to control the electrons within the bond. I think we all know that water is H2O, and maybe in biology you wondered why oxygen, or water, was drawn this way in biology versus this way. Okay, the reason for this bent shape is because the oxygen actually controls the electrons more within these bonds than the hydrogens do. And so what we end up seeing is that the electrons are going to spend more time around this oxygen and less time around this hydrogen. Yes, the hydrogens are being held together through these bonds to oxygen, but the oxygen's greater electronegativity value is going to hog those electrons within the bond.